The talk is called Threading Do's and Don'ts, and it is by Nokia's Bartosz Szurgot.
Okay, so just wait a second. Classic problem. Works better when you turn it on. Okay. So, hello everyone. Welcome to Threading Do's and Don'ts. Today I'll be your guide, so please fasten your seatbelts and enjoy the ride. My name is Bartosz Szurgot, or Bash for short, and I'm a natural-born geek. I break computer software for longer than I can remember, and hardware for longer than my parents wish to remember. Officially, I write software applications for a living, but actually, it would be more accurate that I do it instead of living, but that's probably why most of us are here in the middle of the week anyway, right? So, today I'm going to talk a little bit about threads. This will be a sort of a guided tour through more or less obvious pitfalls related to threading. Frankly speaking, whenever I start a new project that requires some threads, I sort of warm myself up, I say, bring it on, then I imagine a spectacular success and bright lights from the sky and a flawless code since the very first run. Then usually some sort of major disaster occurs and I end up learning new debugging technique. When I finally commit fix, thanks to the version control system, everyone knows that I'm the one to blame. So, what's all about this threading? Is it really that complicated? Let me introduce you to a few examples. You know this guy here? Or here? Yes, this is Herb Sutter. While performing an atomic weapons presentation, he said that when he is creating an object and assigning to some temporary pointer, and then inserting a full memory barrier, and then assigning this temporary value to a global, assuming, of course, the assignment itself is atomic, this is fine. But if you would replace the standalone memory fence with a release fence, there would be a problem, because this assignment could go up, and then it could be reordered with the creation of the object. So we would have then a data race. But this is not the way the standalone fences work. Actually, standalone memory fences are deliberately designed to prevent this type of situation, so this assignment would never kick in before the fence. So this example actually is fine. Another interesting case by Hans Boehm, threads and shared variables in C++11. This is, by the way, the excellent introduction to C++11 memory model. Imagine some sort of lazy initialization. You have the init value that protects x from being initialized multiple times, and you are running this concurrently into threads. So one thread checks if it is initialized, another one does the same. They both lock in mutex, they check if it's initialized, then assign x, assign init d, and then read. So another thread, when it enters, it may skip it. But you can see that there is a data race. How many of you can see the data race here? Okay, quite a few. Good. Okay, so the data race is on init d, because you can actually, one thread can be checking the variable, while another one, under the mutex, will write it. So this is clearly a data race. And Hans says that, we can work around this problem by making init d atomic bool variable. So of course, we will not have this data race. And he says that this program is data race free. How many of you can see a data race here? Raise your hands. Okay, quite good. Okay. I emailed the problem here is on x variable. So if both threads will enter the conditional, one will lock the mutex, other one will block. One will proceed by setting x and init d. Then it will exit, mutex will be unlocked, and then we'll read from x. Then the another thread will lock the mutex and write to x. So we have now a data race on x. I emailed Hans about this, and he admitted that, yes, the example is actually oversimplified. And he said that interesting thing is that I emailed him almost 2 years after he held this presentation. And he said that I was actually the first one to notice. No one before noticed it, even though this was an international presentation. And of course, let him who is without the sin cast the first stone. So this is a short list of multi-threaded errors and mistakes I have made in recent years, at least the ones I remembered. We won't go through full the list because we would probably need to wait like 4 or 5 days for people from last row to get their telescope from eBay. But the point is, there are quite a few of them. So this is really tricky. So concurrency. Probably the funniest comment in version control system I have ever seen was small fixes to prevent blue screens, which is exactly adding synchronization here, 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 and here, and application no longer crashes. So it points out how non-trivial it is. You have a huge amount of code, and it's just enough to fix it in 1 or 2 places, and it suddenly starts working as it should. It is also attention demanding. How many of you know Free Lunch is Over article by Herb Sutter? Okay. Okay, for the rest of you who haven't read, do it at home. Excellent introduction. The general idea is that we no longer can assume that a single CPU will get faster over time, so we write our software, it's working very slow, but we don't care because in 2 years we will have CPU twice that fast. Not really. In 2 years' time, we might get CPU with twice that many cores. So actually, if we want our application to run fast, we need to deliberately take actions toward that direction. So our application needs to scale to the cores. So this is not an academic problem. This is the reality of how we write software today. And speaking of the hardware, it actually gets more and more complicated. This is a piece of dice with Haswell chips compared to the pin size. Even though it's so small, there are lots of heuristics done inside. There are caches, write-ahead buffers, and if you do not know how these things work, you can literally kill the performance by doing some simple mistake. And even if your program is correct in terms of functional requirements, it may work terribly slow. So this is something you really need to care about. Okay, so as a warm-up, let's start with pseudo-random number generation. This is a simple sequential problem. This is, by the way, a case study. A friend of mine once showed me this. This is a pseudocode of actual scientific project that was doing some random simulations. And it just needed to have the average result out of many, many, many computations. And it was taking ages to compute. So a friend of mine was asked, you know, you are good with threads. Can you try to, I don't know, optimize it to make it run faster? And he noticed like, oh, okay, we can actually make it parallel. Because the nice observation is that we are dealing here with something that looks like a pure function. It doesn't really depend on a counter on the loop. So it should be, we should be able to run these functions independently. And actually, each run of the function takes roughly the same amount of time. So it looks like we have a perfect parallel problem. So it should be enough for us to, if we have 4 cores, then we create 4 threads. Each one will do 1/4 of iteration, and we get 4 times speedups. Okay, great, looks fine. So the modified program looks like this. And you can see that this is actually the very identical program that I showed you on the previous slide, except for this line. This is just 1/4 of the iteration. And that's all. It was that simple, right? Okay, so a friend of mine decided to do some measurements. And actually, the parallel version was slower than the sequential one. He thought that maybe these are some strange effects, so he tried more and more cores on different machines. And actually, the more cores he added, the slower the execution was. Something was definitely not right. So he fell back to profiling. Okay, so he has seen that the CPU load is low, and most of the time, application was waiting on a single mutex. And then logic kicks in. Mutex? There was not a single mutex in that application. What the hell is going on? So what was the usual suspect? Simulate random environment. It appeared that the original author wrote this using a POSIX random function, which is, by the way, guaranteed to be thread safe. On that particular implementation, it was done by locking a mutex. So effectively, what a friend of mine did, he wrote a program that one thread was processing data by getting a random number. Other 3 were blocked because they also wanted some random numbers because there was so much randomness done inside. And when it was done, another thread kicked in and was trying to get an extra random number while the first thread was blocked again. So effectively, we had a program that used threads, but in fact were sequential on that particular mutex. So how to deal with it? Drop the problematic random and add a per thread pseudo-random number generation algorithm. In C++11, this could look like this. We'll assign a uniform int distribution on long numbers. We'll create a random device so that we'll have some initial seed for a Merchant Twister. Then we'll initialize with the seed. We'll create distribution from 0 to randmax, which is what original random function did. And we'll have also a lambda called random that will return the next pseudo-random number so that we do not actually need to change the remaining part of the code. And the problem solved. Just this simple modification solved all the issues. And the program really started to scale on cores. And it started to work fast. So, what are the lessons learned from this? First of all, measure. Measure always, and especially measure the obvious. If you looked at the original assumptions, we had a function that was a sort of a pure function, at least at the first sight, and it was taking the same amount of time each time. So, actually, what do you want to measure? Perfect problem, just make it parallel and put to production, right? But it appears it's not always so obvious. So, there is really no excuse for not measuring. Also, avoid shared state. What actually killed the performance was this one single mutex inside the random variable. So whenever you are synchronizing, you are locking. And when you are locking, you are blocking. Because for a certain amount of time, you switch a perfectly parallel problem to the sequential one. And in this particular occasion, this was done so many times that effectively we had a multi-threaded sequential program, which didn't work. And of course, use the state-of-the-art tools. There usually is a way, a mean, why it was introduced in the first place, right? When it comes to the random number generation, if the original author of the original code had used this local generator in the first place, this problem would never have occurred, and I would have like 5 slides of presentation less, right? Which actually would be good. Okay, so we know that sharing is not really that good, so now let's try not to share something. This is a simple source code. We'll have 2 variables, A and B. That will be globals. Thread 1 that will do 10 millions, some computations, and it will increment the value of first variable by the result. And thread 2 that will do 10 million, some different computations. Let's assume they take roughly the same amount of time, and assign it to B variable. And of course, we can scale, so we can add more and more variables and more functions that will operate on them. The point is that these 2 guys are independent. Okay, program is definitely data race free. It is correct. When you run it, it will always return a proper result, so it's deterministic. It's fine. But the problem is, it doesn't really scale again. So we would expect that adding cores, adding threads, as long as we have cores, will have no effect on the time, because we do more computations, but we have more threads to do it, and again, they are independent. In fact, we got this. So we can see that each and every other thread causes program to run slower and slower and slower. So, okay, perhaps allows the CPU. Let's give it a try. 32-core machines, different one. Again, we expect a flat line, yet we get a function like this. So we can clearly see there is a problem here. So let's have a look at the most important part of the source code. These are these 2 things. Do you remember Scott's presentation? Okay, so? Exactly, false sharing, yes. This is exactly the point. False sharing is back in town. So here we have global variables that will be consecutive in memory. So when they will have consecutive addresses, they will most likely hit the very same cache line in multiple CPUs. Since CPUs work in the matters of cache, like 64 bytes, this is very common for modern architectures, and they start with the aligned addresses, the memory could look like this. We have a memory region. Let's say X is an aligned address. We have CPU cache line, which starts with X. Then we have our 2 variables from main memory, and then the Y. Let's assume this is the address of the end of the cache line. And CPU 2 will have exactly the same view, but it will just use different variables than the first one. So effectively, we'll get a hotline between the caches. The caches will invalidate one another over and over again. So we have a classic case of false sharing, even though we do not use any tables. So what can we do about it? Yes?
Do you know if that false sharing occurs in monadic languages?
The problem is really hardware related. So whatever language you will choose, you may fall into this. Yes. Mm-hmm. Okay, so solution number 1 is the art of war style, so defeat the enemy without fighting it. Well, in short, avoid situations like this. So if you are using, again, local variables instead of globals, you actually can achieve that. But it's not always the case. So whenever you have to choose some sort of global or shared state, well, you are almost sure to hit the problem when you're using the arrays, exactly as on Scott's presentation. You remember the example, right? Okay? But it will also hit the case like I've just presented when we have globals in a single file, but that's not over. You are very probable to have the problem if you have globals in different compilation units. And when the linker binds them together, you may end up in having two variables consecutive in memory. So we will have the problem. And the funny thing is that it may be hard to reproduce. So for example, assume you work with some colleagues from different continents, and they say, your application sucks, it's just so slow, you probably have full sharing. You say, oh, okay. You compile, you run the program, and you say, no, it runs 10 times faster than yours, so your compilation is wrong. And actually, you can both be right. Because depending on random values, like for example, how the code will be compiled and linked, you actually may end up in two different builds, in two different configurations of the variable inside the globals the part of memory reserved for global variables. So actually, each compilation may yield a totally different result when it comes to performance. Both will be fine in terms of functional, but the performance will differ dramatically. Also, you may hit it when it comes to dynamically allocated memory, but this is quite unlikely to happen. But technically speaking, yes, it is possible. You can allocate the one address and then get another object which will be next to one another. So there will be a fault sharing as well. So generally, assuming this will not happen is a sort of a risky business. So what you can do is solution number 2, ensure this will not happen. How we can achieve it? The problem was that there are two variables inside a single cache line. We know that the cache line starts with the aligned address, and it has a certain length. So actually, what we can do, we can declare a type that will put our variable at the aligned address and add some padding at the end to make sure that no one else will kick into our cache line. So effectively, our variable will take whole cache line for itself solely. So in memory, this would look like this. So first variable will start with aligned address, then there will be some padding until the end of the cache line, and the other CPU will have another variable, again start with aligned cache line, and up to the end. So this was one cache line, this is second cache line, everyone's happy because hardware no longer need to fight for the resource. So how we can do this? There is a helper template I called cache line that will take type T, which will be our defined type, and alignment. By the way, where does this magic variable come from? Yes, exactly. This is the most probable cache size line that you will have on your CPU. But in fact, this is just the default value, so we can change it. So what happens here? First of all, we do the static assert on type T. If it is POD, plain old type, why is that? Is it required? Yes, but is this really required? Or we can just get rid of it and live happily? Please speak up. No, you just have one single variable inside, so nothing can happen here. Thank you, exactly. If T is not a trivial type like, I don't know, int, double, or so, for example, let's take string. What will string do in a constructor? It will allocate the memory. So we will have perfectly aligned pointer to the string, and then a string which can actually hit the false sharing case, right? So this is really not what we wanted. So to ensure that no one makes that mistake, we just static assert. If someone puts the wrong type in here, it will just not compile. So great. Okay, so we have this variable, and how to make it aligned? There is an align as keyword in C++ 11. Scott mentioned this, right? Come on, guys, wake up. Oh, okay, thank you. And we know that the first member in the structure will always have the same address as a structure. So when we are aligning a cache line, it effectively says that this variable will be aligned. And what about the padding I was mentioning, right? I said that we need to pad it as well so that another variable will not kick in our cache line. In fact, it is not needed. Why is that? If we are saying we are aligned to some size, let's say 64 bytes, then we effectively tell the compiler that it needs to create an object that if we will take array of these objects, and they will be next to one another in the memory, each and every needs to be aligned. So this is the case where a compiler needs to add the padding by itself. So if there would be no padding, and we were creating the array, just give me a second, and we'll create the array, actually the x+1 object would not be properly aligned. So in order to keep it, compiler needs to add the proper padding here. Yes?
If you have the cache line with our variable and then, like, for example, boolean, the current global is the same file, we can just step into sharing
Let's assume for a second that this is our cache line template from the next slide. Okay, so we start with the aligned address, right? So this will be always the beginning of cache line, some cache line, right? So whatever is here or here after the padding doesn't really concern us. Mm-hmm. Yes, the question was if it's 64 bytes long, then if the next element can be, yes, it can, but it will occupy a different cache line, so it's not a problem. Yes?
How we can be sure that our structure is allowed from the beginning of cache line?
Beg your pardon?
How we can be sure that our structure variable
Okay.
at the beginning of
So how can we assure that the structure will be at the beginning of the cache line? Sorry. This is exactly what the align as is doing. It says that this structure needs to be aligned, and the first member of the structure will be aligned as well then. So,
management part, and then the heap allocated part is just random, so it's also okay from the fault sharing point of view, right?
when it comes to stack allocated stuff, there is no problem. The problem is when it's global, it's most likely not a problem, but when it's global or heap allocated, this can be a problem, and for this stuff you will need the cache line. So in fact, if you would like to use a string constraint with the cache line, you would actually need to implement the string that will keep the data, its internal data within the structure. So this would be a character array of a given size. Okay? Okay.
Is it correct to assume that we can achieve the same effect by placing data into different memory sections and playing with linkers?
Yes, you can, but then you need to have a control over each and every variable, because it's not enough to say that your variable is in this section and starts with this address, because someone might put accidentally a variable that will kick into your section. So you'll have the problem again. But this would also be quite an effort to deal in a project that has, for example, 2 million lines long. Okay, so let's see our template in action. So originally, we had this chart. After implementing, we have this. Exactly, almost the ideal, perfectly flat line. So we can see this is the things improved. But again, did we get lucky? Let's say at our 32-core machines. No, we didn't. We actually solved the problem. We can see that here the line is not perfectly flat. This is probably due to some memory latencies because, well, we are using 32 cores that intensively read and write the memory. So this might be the effect. But generally, the problem is solved. Okay, so what are lessons learned? First of all, measure. This is really the most important, and this will be a key of this presentation indeed. Think about the caches. Caches are actually our friend. They make application runs faster on the hardware that costs roughly the same. So they're great speed improvement, but the worst case scenario is do the cache miss or false sharing or other messing with caches. So you need to be aware that even though functionally they are transparent, they're not transparent when it comes to performance. Some little modifications in code may affect it vastly. So keep in mind that the more CPUs you will use, actually, the bigger the impact will be. So caches are important. When you are doing a multi-threaded programming, it gets like square of that importance. So it's more and more important the more cores you have, because the higher chance of some sort of a pollution there will be. Okay? Okay, so we tried to share, not to share, and now let's try to do some atomics. By the way, how many of you use atomics on a daily basis? Okay, a few hands up. Nice. Okay, so before we switch to atomics, let's try not to use atomics for a second and see what happens. So we have this piece of code. We'll have a global int counter 0. We'll have multiple threads that will run 1 million operations that increments the counter. We know our hardware, this is x86, and incrementation is just a single instruction, cannot be interrupted, and so on. So should be no problem, right? Okay, so what do you think? Who thinks the program is good? Okay, who thinks it's bad? Okay, and who thinks it's ugly? Okay, okay, the last two groups were correct. So in fact, if you run this program, at least on my machine, on 4 threads, I got these results. So out of 10,000 runs, I got the correct response around 500 times, and the rest was, well, let's say close. So roughly, I was right about 5% of the time. So if getting a correct result once in 1 in 20 runs is okay with you, this is your way to go. If it's not, then we probably need to fix actually a bug. So what happened here? Well, we lied to the compiler. We said that int is just a regular global variable and that we will share between threads, right? And what happened? Compiler did optimize this away because it knows that, well, it's just gcounter plus 1 million and we're done. And we actually can see that we lost some writes to the memory, right? We would expect to have 4 millions, but actually we got sometimes 2, sometimes 3, so we can see that either reading or writing failed. So what do we do if compiler is optimizing our variables? We volatile, right? Okay, so let's try making it volatile. This will disable the optimization. So now we are sure that here we will have 1 million increments of this little guy here. So again, who votes for good? Okay. Bad and ugly? Oh, okay. Not that convinced, but okay. So again, what do we do to determine who's right? Exactly, we measure. So let's do it. I got 3 most popular results out of 1,000 run because the program runs for quite some time, so I got lazy here. The funny thing is that we could actually draw a histogram of possible solutions here. But the most probable version was getting 1 million. 1,060,000 was quite an option. 1,002,000 was also very popular. And actually we got right 0% of times, or actually 0 times, nowhere. Out of 1,000 run, we didn't get it right even once. So the closest result was about halfway through. This is a bit less than 2 millions. So we can see that by trying to fix things, we actually made it worse. So volatiles didn't really help. It breaks stuff. Okay, so actually the only way to do this correctly is to use the atomics. So we create atomic int counter, initialize it, and then we can do 1 million increments in each and every thread. And this will be valid, and we'll always get, from 4 threads, we'll always get 4 millions as the result. Yeah, we got the success, right? Okay, but if you think about this, what do you think about this code? Slow, definitely. Why? Yes, it's even worse than false sharing. This is real sharing. We are actually sharing this between the CPUs. This is no accident. We done it deliberately. Badass, right? Okay. So we should think before we actually code. If we need to have this global counter that needs to be updated, the question is, do we really need to have it updated after each and every operation on it? Perhaps we're fine with getting the updated result once in a while. And we could actually replace it and take both the benefits from both of the worlds, the local variables and the shared state that we need to propagate further. So we could copy our original algorithm. So we'll have the local counter and increment it 1 million times and then assign it to a global counter. Okay, if this can be an option, this will be way faster. Why? Well, if you look at this, there are really no variables here. This is a constant value. We know that here at line 7, after line 7, the counter will be will have value of 1 million. So we'll actually need to increment the global counter by a constant value. So the compiler will work for us. It will optimize our code and will do it without breaking anything. Why? Because we didn't lie to it. We said that this is a counter of integers, but this is shared, and the compiler should be aware of this. So if this is an option, you should go this way, because it is way faster. Okay, so we know that with volatiles, there are quite some problems, right? We can have lost writes. There will be certainly missed optimizations because we just say to the compiler that we need to read and write to the memory each and every time. We have seen that even a single instruction, like incrementing or summing, did fail. So let's try to go for a rescue mission for volatiles and see if there's even a single scenario that could actually work on modern hardware using the volatile flags. Okay, so we know that writes or reads can be lost. But let's think for a second. Okay, if we were using just just for signaling, so we'll have this global bool variable, and one or more threads will at certain time just assign true to it. Even if some of these assignments will be lost, effectively at least one will get to the main memory, and the other thread sooner or later will realize that the value has changed, right? Why not? Okay. So we write an application. We'll create two volatile bools, started 1 false and started 2 false, and we'll try to create an algorithm that will say which of the two threads started first. So thread 1 will assign true to started 1, and then we'll check if thread 2 was not started yet, and if not, then we know, okay, thread 1 was started. Thread 2 will do the exactly opposite. It will set started 2 to true, and we'll check if thread 1 was started or not. And if it wasn't, then we know that the thread 2 has been started. What are the expected results out of it? What do we expect to see on the screen? Okay, so definitely we can see thread 1 was first. Okay, we expect to see thread 2 was first. This might happen. On very, very rare occasion, it also may happen that none of this will be printed because both variables will be set to true and both conditions will fail. This is fine. Okay, so, okay, we have an experiment. What do we do? We measure, okay. So, most of the time it's fine. But about 6 times in 10,000 tries I gave it, I got the result like this. Thread 1 was first and thread 2 was first. So, we definitely have some sort of a cognition problem here, right? So we got error rate of 0.06%. Now try to find this on a production from a bug report from clients. You know, every 2 or 3 months our application crashes and we do not know what it is. Can you look at it? Yeah. Yeah, exactly. This should be the response, right? Why? Wow, how? Okay. So the real question is, what have happened? We definitely haven't half-written bool to the memory, right? Okay. So let's zoom in to our original code, and let's pay special attention to the beginning part. We'll just analyze one thread here. So we'll have two volatiles, 2 bools. Thread 1, assignment, some memory write. Then we'll have some memory read, condition, and so on. And then we have some action. OK, we compile this guy. And then we do not trust the compiler, so we decompile it and check the assembly if it's OK. And we can see that, OK, we have memory write, and then we have memory read. Everything looks perfect. So what could be the problem? We definitely see a wrong result. Well, the point is that we again lied to the compiler and did not say that the variables are shared, and volatile disabled the optimization for a single variable only. It says absolutely nothing about the interaction between the variables. And one of the optimizations that both hardware and the compiler are allowed to do is, under certain circumstances, reordering of the instructions. So effectively, our program, even though we checked the compiler did not break anything, actually in the hardware can be reordered, and we actually can get a program like this. So we'll have a memory read followed by the memory write. So this particular situation is possible even on x86, which generally has an opinion of having very strong memory, very strict memory model, and there are really not that many reorganizations that you can have at runtime. But this is one of them, and it actually spoiled our algorithm, but just 6 out of 10,000 times, right? Not that bad. Okay, so now we know that compiler can reorder, hardware can reorder. The question is, do they really break our programs? Fortunately, the answer is no. There are certain restrictions on what can happen, what can be reordered. And first, the most important is we cannot see the observable effect of this optimization as long as the program is single-threaded. So what with this multi-threading? Well, if it is multi-threading, we need to tell the compiler that this little guy here and there, they behave a little bit differently because they are shared between different threads, so different threads can change them. So compiler needs to ensure that it will not break it, and to instruct the hardware by inserting certain instructions into assembly that will also tell hardware not to break it as well. And then it has a chance to work. So actually writing a data race-free program, so the program that doesn't race, we always say properly what is synchronized or not, is actually a must. If we don't do it, we can get the weird effects like just shown before, some random reorganizations, random faults. You can notice that the program was really simple. It fitted on a slide. It was like, I don't know, 15 lines long. Try to find something like this in a program that has 2 million lines of code and 20 threads running simultaneously. This is a rough challenge, right? So if we have a data race-free program, we have this thing called sequential consistency, which basically says that we will not get this observable effects of multi-threading as long as we do not lie to the compiler about what is really shared and what is not. Okay, so what are lessons learned? First of all, never ever use volatiles with threading. These are totally different concepts. Volatiles are for usually low-level accessing of certain parts of memory. It's often used on microcontrollers when certain parts of memory are mapped to some devices and so on. This is the usage. It has absolutely nothing to do with threading, and never ever try to use it. I mean it. When you need to synchronize, what do? Yeah, no, atomic, mutexes, right, conditionals, whatever you need, but you need to specify them explicitly. Okay, so keep in mind the sequential consistency. As long as you are on the good side of the force, you're fine. When you will step the line, it will bite you sooner or later, and it may happen really spectacularly. You will get the problems that you will be absolutely unable to reason about what actually happened. You can look into assembly, and still you won't see what's the problem. So avoid this at all costs. Also, might be efficiency. As shown previously, by just simple reorganization of our code and using local variables as much as possible, we can significantly improve our algorithm. So instead of thinking how not to share, what to share, or atomic or mutex, just think about, okay, I will use local stuff and I'll be fine. I'll be on the safe side. And just as the final step, I will write it to this shared part of memory, which for some whatever reason is really needed. And experiment and verify. We're already talking a little bit about measuring, right? But there is also one more thing, code review. You all do code review, right? Hands up, who does code review? More hands, please. We will be working together one day probably. Come on. Okay, so the code review is actually, from my point of view, the best way of finding such problems, because even though you can have a random crash 1 in 10,000 times, actually, having a code review for someone who is experienced with threads and hardware will be of a great beneficial, because it is easier sometimes to spot the problems on the source code level than it is to try to debugging it when each and every time you run it, it behaves differently. So code review is always important, but when it comes to threading, it's double the importance of this procedure, at least. Okay, so the short summary. If I were ask you to remember 3 things from this presentation, this would be. Exactly. This is my point. This is the single most important thing I want you to remember out of this presentation. Always measure. Also, be cache aware. You need to know at least roughly how the caches work, not to keep shared data in a single cache line, and always prefer local over global or any other form of shared state. Because it is easier to reason about, less error prone, and also way faster. When you need to synchronize, do it always properly. Always go through the data race free. So signal what needs to be shared. Never ever use volatile. If you see a volatile in a code review, don't read it. Just say, okay, this is a problem. This should not happen in a multi-threaded application. Just go and fix it, because it's really no point in continuing the discussion at the point. Once you do this, you will benefit from sequential consistency. So again, you will be able to understand your programs, which is, well, quite important, right? Okay, another homework for you. Please read a C++11 memory model part of the standard. This is literally half-page long. It's that short. And also read multi-threaded executions and data races. This is about 4 pages in standard. And after reading this, you will have a really good understanding of what is allowed and what is not. When you need to synchronize, when you do not need to synchronize. And also, keep in mind that even though most of us work on this architecture, which is, well, quite understanding towards our mistakes. There are also others like ARM or Intel Itanium. Intel Itanium, which both of them have pretty weak memory model. If you are actually talking about Itanium, okay, this will be probably a bit abstract for most of you, but actually when it comes to ARM architecture, you have at least one CPU like this in your pocket. So this is very important, and this is not an academic problem, because some code that is incorrect and runs on x86 correctly, because x86 as the hardware adds some extra restrictions on what can be reordered at runtime, this may fail spectacularly on ARM or Itanium. Okay, when it comes to some materials, I highly recommend you watching Thread and Shred Variables by Hans Boehm. I mentioned it in the beginning. This is an excellent introduction to C++ memory model. So if you do not want to read, just watch it. It's about 1 hour, and it will really give you the great overview. When it comes to atomic weapons by Herb Sutter, this will probably be the best choice for start. And of course, CPU caches and why you care. Thank you, Scott, who have been on Code Dive. This part of homework is done. When it comes to reading, there is a sort of a Bible, C++ Concurrency in Action, Practical Multithreading by Anthony Williams. So after reading this book, you will probably know all you need to really know to work on a daily basis. And I also highly recommend The Hitchhiker's Guide to the Galaxy by Douglas Adams, because this is just so awesome. Okay, that's all from my side. Okay.
In case you didn't realize, that big question mark means that Bartek will now take some questions, not many though. The gentleman over there, please.
When we were talking about alignment of variables in cache lines, so we might resolve it in this particular situation, but because we lost a part of cache memory and cache is limited, don't you think that it will not work in real production environment with multitasking?
Okay, these are two things to address. First, yes, you are definitely right. This is a sort of a trade-off. You ensure you will not hit the performance in certain situations, but you are losing a memory. And you may say, oh, okay, like 60 bytes, who cares? When it comes to cache, you do care. These are kilobytes and megabytes, right? So you do really care about them. So here, we can actually fall back to one of the previous statements I have said. Try to do local work as much as possible. If you will do infrequent writes to the even shared state, this will be no problem. Even if the parts of the memory will fall into a single cache line, this will be no problem as long as it doesn't happen too often. So first of all, try to localize your data, and perhaps you will not need the solution. But if there is a problem and you cannot solve it other way around, and you need to be protected against the false sharing, then sorry, you need to lose some part of the memory. Okay.
Person
Who
over there,
has
and
mic?
then,
Hands up.
and then gentleman over there.
Okay.
Who's first?
No, hold on.
On the left.
Over there, and you're next.
On the left.
Can you please stand up? I cannot see you. Ah, thanks.
Okay, so I will advocate the devil, because you don't always have a luxury of C11, and
Beg your pardon?
you don't always have the luxury of C++11, and now you have to work with something else, and volatile. Which, of course, you are correct all the way up, works only because on some exotic machines there are no caches, no out of order executions, and so on and so, and there volatiles works. Of course, it works by mistake, because it was never...
By accident.
Yes, by accident, but I only wanted to note that multi-threading was before C++11,
Okay.
but it was on...
So what to do on pre-C++ 11 code, right?
Yes,
That's
yes,
the
yes, yes.
question. Okay. So frankly speaking, C++ 11 was in 2011, if I recall. This was about 3 years ago. And actually, we were writing a multi-threaded applications long before then. What do? We generally use the external libraries that covered all the magic if given hardware can use safely volatiles or not, if there need to be a certain instructions emitted and so on. An example of this can be POSIX threads, right? So there were means to do it, they were just not standardized and often not that intuitive to use, and usually a C application is a C style, so you needed some sort of wrappers to make sure your source do not leak and so on. So it was a bit more tricky, far less convenient, and there were certain corner cases which were not exactly specified if this would be a data race or not. C++ 11 makes it clear. So if you are doing multi-threading, switch to C++ 11 compiler as soon as possible. Okay, thank you.
Gentlemen over there, please, and if you'd like to keep your questions brief, please.
You said that you can have a full sharing in case of allocation on a stack.
Yes. On a heap.
Yes.
Okay, on a stack, well, yes, you can, but you would probably need to do a little bit of voodoo, like passing a pointers to your local stack data to another threads. Yes, then you can hit it, but generally you are asking for it then, right? When it comes to a dynamically allocated memory, it may happen by chance. Okay?
Gentleman over there, and then you, sir.
Okay, the stuff that you're talking about, manual management of threads, locking, etc. These in the concurrency world, this is extremely low level. This is the assembly language equivalent. When talking about small applications that need to be very optimized, fine. But when we're talking about things that have millions of lines of code, aren't we just better off going to higher level models of concurrency, like message passing concurrency or task-based concurrency, which is in C++11 standard library?
Okay, excellent question. Yes, the mechanism I have shown here are pretty much low level. And yes, indeed, there are, even outside of C++11, there are quality libraries that allows you to do more and a sort of a hide threading behind certain API. And this is good because in many cases, this actually helps you and allows you to avoid problems. So if you cannot communicate to another guy by throwing a pointer at him, but instead you need to send a message, then by design, this message will be sent, it will be copied somewhere, and the guy will receive a local copy of this message. So then, in sort of systematic way, you just avoid a sharing state. The problem is when you are writing a very high performance part of the code, and then you just cannot at all a luxury of all these abstractions on top of what is actually happening within the hardware, because these problems are actually hardware related, right? So yes, if you can, please do this. This will save you hours of debugging, and it will just make your life easier. Yeah, that's fine. It's as long as you are fine with certain penalties in terms of performance, it's perfectly fine.
Last question over here, please.
In your professional experience, have you had any chance to work with property-based tools, tools for property-based testing of concurrent code, and if so, what are your comments on that?
Well, when it comes to tools for testing, okay, two things to set straight. You can have testing in means of unit testing, model testing, and so on. And when it comes to this, well, here we are actually mostly testing functional part. So there is very little chance that with using these types of tests, you will notice these types of the problems I have mentioned here. When it comes to tools that help you detect errors, I actually use Linux on a daily basis, so when it comes to proprietary software, it's a bit more difficult.
Yeah, but something like QuickCheck, for instance.
Beg your pardon?
Like QuickCheck, which, as far as I remember, was for Haskell or Erlang, but...
I'm sorry, I'm not familiar with this tool. The one interesting tool that I have seen in action was Intel's Parallel Studio, and this really could detect a lot of data races on your program. So effectively, you could take a single threaded application, run it on multiple cores without any synchronization, and then it will point it out that, okay, this thread and this thread is reading and writing this variable, so you need to synchronize here. So yes, you could do this. There are tools for that, but keep in mind they are not perfect, and they will detect the situations that actually will occur. If you will have a situation that is extremely rare, you will most likely not notice it. So again, probably doing the pure code review by an experienced person is actually the best approach here.
Providing questions to your answers and doing the talk about threading do's and don'ts was very own Nokia's Bartosz Szurgot.